Alright, so this is going to be our second video about the Laplace transform. We've already discussed the general idea behind why we're talking about it and how we're going to use it to solve equations, and in particular to solve equations that the other methods can't really deal with. These are with impulsive or impact forces that are applied to an object in harmonic motion, for example. This video is just going to cover, we're going to go through some of the formulas related to Laplace transform. So we have an idea of how we can use these formulas to do the work for us. There's no reason to reinvent the wheel all the time and keep computing the same thing over and over again when you can basically compute it once for a general situation. And then you just have to plug in your specific function into a formula in the appropriate way. So we have this claim here is we have this formula that the Laplace transform of an exponential times some function f is just the Laplace transform of that function f shifted by that number a in the exponential. So this is an easy observation. We just plug this in. This is just the definition of the Laplace transform of this function. All right, there's my function I'm computing the Laplace transform of. I have to integrate it from 0 to infinity times this exponential e to the negative st. So s is our new variable, a is some fixed number. So exponentials go together, just with rules of exponents. So now what we have is we're integrating f times some exponential e to the negative something t. So that something is the input of our Laplace transform of f. And that's it. That's all there is to it. So there's an inverse property. If you have a function of s which looks like a function where you're plugging in a difference like s minus a or s plus a, then you can realize that the inverse Laplace transform of that is going to be just the inverse Laplace transform of the function f you're talking about multiplied by the appropriate exponential. So for example, a constant function. The function is just 5 or 10 or 1. In this case c. Compute the Laplace transform. This is a simple Calc 1 integral. We're just integrating e to the negative st. We just pulled the c out, and basic u substitution here. Remember, t is our variable. So what this line means is when we apply the fundamental theorem of calculus, we're integrating all the way to infinity for t equals infinity. So we don't really plug in infinity, but you can think of it that way, because e to the negative st is decreasing to 0 as t goes to infinity. So that number which I'm writing is e to the minus infinity s. What that really means is we know s is a positive number. So this is like the limit as it's the limit as the input of e to the negative something is going to 0 as that input is going to infinity. So it's 0. And e to the negative 0s is just e to the 0, so that's 1. So we'll get a minus 1 and the signs cancel. So the point is the Laplace transform of 1 is just the function 1 over s. The Laplace transform of 10 is 10 over s. That's linearity. The Laplace transform of negative 5 is negative 5 over s. But our previous formula, the one we were talking about, the Laplace transform of an exponential is just the same thing as that exponential times 1. So we just take the Laplace transform of 1 and we shift it by a. So 1 over s becomes 1 over s minus a. And again, this integral above only makes sense if s is restricted to being bigger than this number a. Again, if your a is a negative number, for example, you would have a plus here. If it was negative 3, you'd have 1 over s plus 3. So now we have another formula. What if I multiply a function by a power, an integer, positive integer power? How does that result transform into something? And what we're saying is each power you multiply by before computing the Laplace transform amounts to a factor of minus 1 and a derivative of the Laplace transform. So multiplying by t before applying a Laplace transform, that transforms on the side of the Laplace transform into a negative derivative. So let's just see this for the first power t, which is n equals 1. So remember, capital F is the Laplace transform of lowercase f. So negative 1 to the n, I'm just copying negative 1 to the n. The nth derivative, I'm using new notation now because it makes more sense to use this notation, nth derivative. And then in parentheses, all this stuff is just capital F of s. All this stuff here. I'm just plugging in what we have. Because these integrals are such that they always converge, we're always using functions which make this converge. This exponential decay makes these integrals converge. You can commute derivatives with integrals. So I can pull the derivative in s inside because s is not the variable that we're integrating in. It's just a fixed number. So I pull that inside, and what I'm really doing, I'm just differentiating n times this exponential. What happens when you differentiate an exponential? Because the function is in s, we have a negative t times the s. So every time I differentiate, I'm going to get that exponential back times a negative t. So each time I do it, I pick up a factor of negative 1, and I pick up a factor of t. Since I do it n times, I combine all those powers of negative 1, and I get negative 1 to the 2n, which is an even power. So that's just 1. And what am I left with? I'm left with the Laplace transform of t to the n times f, which is what the formula is claiming. And again, all these formulas come with an inverse formula. Here I'm moving the negative 1 to the other side of the equation. Remember, when you divide by negative 1, it's the same as multiplying by negative 1. So I'm not writing it as 1 over negative 1 to the n. I'm just writing it as negative 1 to the n. So what does this formula tell us? Well, it allows us to compute the Laplace transform of all power functions. So remember, the Laplace transform of the constant function 1 is just 1 over s. So since t to the n is just t to the n times 1, we're thinking of lowercase f as our function 1. Our capital F function is 1 over s. So Laplace transform of a power function, t to the n is just, by the formula, negative 1 to the n times the nth derivative of 1 over s. But 1 over s is s to the negative 1 power. So every time I differentiate that, I'm going to take the negative 1 down, negative s to the negative 2, then times negative 2, s to the negative 3. Keep track of all that. You're going to get again, these negative 1s are all going to cancel each other out. And what you're going to end up is like the negative 1 times negative 2 times negative 3 and so on. That's a factorial that we're going to get. So we get this n factorial. We're like n factorial, 3 factorials, 3 times 2 times 1. 5 factorials, 5 times 4 times 3 times 2 times 1. And then after we've differentiated 1 over s n times, we have a power negative n minus 1. So that just simplifies this to what we have here, n factorial over s to the n plus 1. So Laplace transform of t is 1 over s squared. The Laplace transform of t squared is 2 over s cubed. The Laplace transform of t cubed is 6 over t to the 4th, and so on and so on and so on. Again, combining this with our formula where we multiply a function by an exponential, I'm just multiplying t to the n by an exponential. So I'm taking the Laplace transform of t to the n, and I'm going to change the variable s to s minus a. That's all we're doing. So now we have those as well. Sines and cosines are a little more complicated. The details, I think, are actually in your book if you want to look at them, but it's just integration by parts. So if w is some number, like 5 or 6 or 2, and it could be anything, that's fixed. So this is just the Laplace transform of the sine of wt. And when you work it out, it simplifies quite nicely to whatever that constant w is, divided by s squared over w squared. And when you do the cosine, it's a very similar calculation, but what happens is instead of w in the numerator, you get s. Again, these are just integration by parts, And these are just some formulas to recognize. You want to recognize these when you see functions that look like this. All right, because then you'll know when you take the inverse Laplace transform that it's a sine or a cosine function. Now, probably the most important one we're going to use, but we're actually only going to need to use it once, because we're going to basically come up with a formula for solving second-order equations. And once we have that formula, we will use this formula for that. We'll never have to use it again for the second-order equations. But it's an important one to observe. When you compute the Laplace transform of an nth derivative of something, let's just look carefully at what we have. The first term is a power times the Laplace transform of f. And then we have to subtract off a whole bunch of terms. We subtract off lower and lower powers of s times higher and higher derivatives of f evaluated at 0. So s to the n minus 1, f prime of 0. I mean f of 0. And you can think of f as like the 0th derivative. And then we have n minus 2 and the first derivative at 0. And it keeps going that way until we get to s to the first power and the n minus 2 derivative at 0. And then s to the 0 power, which is 1, times the n minus first derivative evaluated at 0. Let's look at for just one derivative, n equals 1. All we do, we integrate by parts. Okay, we're going to let u be e to the negative st, and let dv, it's the derivative, it'd be the derivative, f prime. Using integration by parts, I get u times v, evaluated from 0 to infinity, minus the integral 0 to infinity of v, which is f of t, du. This is the derivative of e to the negative st. Now the negatives cancel. The s is just a constant. It comes out front. And what we're left with is the integral of this, which is just the Laplace transform of f. In other words, we get this, which is exactly the formula we have above when n equals 1. All that happens when you have higher order derivatives is you just apply this formula over and over again to get from one derivative to the next lower one, and then you keep applying it. Every time you apply it, you pick up an extra term involving the evaluation of some derivative at 0, and it works out to what we have above. So just summarize. A is some number fixed. We have to, whenever we have this exponential a, we realize that s has to be restricted to being bigger than a. T is some fixed positive value, and w is some real number, and n is some positive integer. So we have our powers times exponential formula. If that's our function, then it's Laplace transform is over here. We have our sine times an exponential. Again, we just took our sine Laplace transform and translated it, shifted s by a. Cosine, do the same thing. Take our cosine Laplace transform, shifted each occurrence of s by a. Generally, a power times any function is negative 1 to the power n. So n is odd, it's negative. N is even, it's positive, times the nth derivative of the Laplace transform of whatever that function lowercase f is. Now, there's a kind of inverse to that one, which I'm noting, but I don't really, you may run into needing to use it, but it just says that if you, instead of multiplying by a power inside the Laplace transform, you divide. Well, multiplying kind of corresponded to differentiating, so dividing by powers of t should correspond to anti-differentiating the Laplace transform in some way. That's what this basic integral is doing. It's kind of an antiderivative, but it's a negative something. But that's the idea. And then the derivative formula. We basically get the power corresponding to the number of derivatives times the Laplace transform of f. And then we have to subtract off all those terms, which are just increasing powers of s times lower and lower order derivatives evaluated at 0. And this is just some summation notation to say, add up all the terms that look like this, where j ranges from 0 to 1, 2, 3, 4, up to n minus 1. And that's for this video, just basic formulas, and we'll use them in future videos. And when you get to your homework, I will outline these things very clearly for you, because there's so many formulas that really aren't going to master this in the first course. I said before, this topic of Laplace transform could make up a course in itself. So we're just going to kind of understand the basics, and I'll kind of walk you through how to use these steps so you can solve some problems.